In this video, I'm going to talk about second order linear differential equations with constant coefficient. For this type of equation, we are going to consider that e to the power mx is a solution. Then we can substitute into the equation. So we take the second derivative of y, first derivative of y, and once we substitute, we get a m square plus b m plus c equals 0. And this is a quadratic equation which is called the characteristic equation of the differential equation, and this quadratic equation can be solved for m if we know a, b, and c, and then we can get the fundamental set of solution. So this is discussed in details in another video, how to derive this characteristic polynomial, which is not the topic for today. Take an example, second derivative of y plus 3 times y prime plus 2 times y equals 0. And here a equals 1, b equals 3, c is 2. And obviously we are going to assume that y e to the power mx is a solution, and then we can substitute it and we can get the characteristic equation. So generally it is straightforward to think what could be the characteristic equation, and by looking at the derivative and their coefficients, so m square, for the second term we are going to get bm or 3m and plus 2 equals 0. And you can see that this quadratic equation is straightforward to factorize, and you don't need the quadratic formula. We can write m plus 2 m plus 1 equals 0. I can factor it out, then set each factor equals 0. So this leaves you with m equals minus 2, m equals minus 1, and hence you have two solutions. One is e to the power minus 2x, and the other is e to the power minus x. If you wish, you can write the fundamental set of solution using a curly bracket, and which one you write first, e to the power minus 2x or e to the power minus x, it doesn't matter. And now once you know the fundamental solution, you can write the general solution, which is a linear combination of the fundamental solution. So c1 e to the power minus 2x multiplied by a constant c1 and plus another constant, which is c2 e to the power minus x. And this general solution is a two-parameter family of solution. We need additional conditions that will be discussed later to determine the value of c1 and c2. Hopefully this example helps you to understand. Now I'm going to consider a very similar example. So this time I'm going to take a number 2 for the coefficient of second derivative, and I'm going to assume that e to the power mx is a solution. I will substitute e to the power mx for y. So y double prime will be m square e to the power mx, and e to the power mx clearly will be cancelled out. 2m square 3m minus 2 equals 0. This is my characteristic polynomial for this differential equation, and you can now use the quadratic formula. You can factor out if you want, but maybe for this one using the quadratic formula is not too bad. So minus b plus or minus root over b square minus 4ac, 4 times 2 times 2, 16 divided by 2a, which is 4. So 3 plus or minus 9 plus 16 is 25. So then you can write 5 plus 3 is 8. 4 times 2 is 8. So this is one solution. The other solution, 3 minus 5 is negative 2. So you get negative half. Okay. So then your fundamental set of solution is going to be e to the power 2x and e to the power minus half x. You can write y2, and the general solution is c1 e to the power 2x plus c2 e to the power minus half x. So hopefully it is clear. Take another simple example before we go to do a complicated problem to understand that whether we are understanding the process. So it is the same thing, but this time I'm going to set a y double prime. A is 1, b y prime, b is minus 5 plus c y, and c is 0. Just two terms. So obviously you get the characteristic polynomial, and then you can write m times m minus 5 is 0. So m is 0, m is 5. Okay, so then you have a fundamental set of solution e to the 0, which is 1, and e to the 5x. Okay, so then your solution is, general solution is c1 times e to the 0, which is 1, or c1 times the first solution, which is 1, and c2 times the second solution, e to the power 5x. And you see that the solution looks slightly different than the other solution is because m is 0 and m is 5. So the characteristic polynomial has two solutions. One is 0 and one is 5. So what we see that the characteristic polynomial has distinct solutions. But how about other issues? So you think this way, maybe I can write down it here. Say you have a m squared plus bm plus c equals 0. So maybe just to mention what we are doing here, other solutions of the characteristic polynomial. So this quadratic equation will have real distinct roots. So real distinct roots, two real distinct roots, obviously two real distinct roots. Maybe I just write down more specifically, two real distinct roots if the discriminant of this equation b square minus 4ac is positive. So number 2, it will have two real equal or repeated roots. If this discriminant is 0. If the discriminant is 0, now maybe you can think of what would be the other case from a first year algebra or high school algebra course. Two complex conjugate roots when uh, b square minus 4ac is less than 0. Maybe it's a good idea to just indicate with an example what do we mean by a distinct root. So an example of distinct root, we just have something similar, say m equals minus 2, m equals 3. Depends on what value of a, b and c. Real repeated roots would be m equals say 5 and m equals 5. Both roots are equal, so sometimes we say repeated roots. And the complex conjugate could be something like, say, m equals 3 plus or minus I 5, and this I is square root of minus 1. I know that for some of you who are doing electrical engineering, you may not use I for complex unit, so you may use j equals minus 1, which is the unit for imaginary number. So that's also possible to write, but most common in mathematics and physics, most commonly used symbol is I, square root of minus 1. So this first number excuse me, first number is the real part and second number is the imaginary part. So what happens when the roots are repeated or imaginary? That is what now I'm going to show you with few examples, and then I will tell you what to do instead of discussing the theory in advance. So I'm taking an example. Okay, y double prime plus 2y prime plus y equals 0, and again the same way you assume e to the power mx is a solution, so you get characteristic polynomial. Okay, and then you can see that this characteristic polynomial is a perfect square. The perfect square, which is good, but now because it is a perfect square, you can write m plus 1 equals 0 and m plus 1 equals 0. So it has two roots. M equals minus 1, m equals minus 1, which is okay, which is not bad. Then you need to have fundamental set of solution. So fundamental set of solution e to the power minus x and e to the power minus x. Both are the same. So both are same means they're the same solution, and you know that from the theory that we discussed the other time, or maybe watch my other video, that in order to have this fundamental set of solution, fundamental set of solution, there has to be linearly excuse me, there has to be linearly independent, or their Wronskian has to be non-zero. And in this case it is obvious to see that they are not linearly independent, so we have to make them linearly independent. And what we can do, I think one trick we can remember that we can multiply one of the solution by x. I'll discuss another time that why this makes these two numbers, the two functions, linearly independent. But now this is the way we look for uh, when, or we work out when two roots are equal. So then if you write down the general solution, if you write c1 e to the power minus x plus c2 e to the power minus x, again you can see that c1 e to the power minus x plus c2 e to the power minus x is same as c1 plus c2 e to the power minus x, and you can write c1 plus c2 equals c3, so a constant times e to the power minus x. So that does not make a linear combination of two functions or two solutions. So obviously we need to multiply by x. So what do we do when the characteristic polynomial has repeated solution? We just multiply one solution, one member of the solution set by x in order to make them linearly independent. So hopefully this is clear. In order to walk you through better, I am considering another example, and obviously you might have started thinking what would be the characteristic polynomial, what would be the nature of the characteristic polynomial in this case. So if I consider this example, then you see that the characteristic polynomial would be m square minus 10m plus 25 equals 0, and you can factor this quadratic quantity to a perfect square, a minus b whole square, s square minus 2ab plus b square, and this is perfect square. So as I said, you might be thinking what would be the excuse me, what would be the form of a characteristic polynomial in this case when it is repeated root. So it's perfect square. Characteristic polynomial will be a perfect square, and now m is 5 comma 5. M has two solutions and both are equal. So you write the general solution, or maybe just if we want to write down the fundamental set of solution, which is e to the 5x, and I multiply one of them. It doesn't matter which one you multiply by x, it is the same thing, and then you write down the general solution c1 e to the power 5x plus c2 x times e to the power 5x, and be careful, don't forget to multiply by x to one of the number. Okay, so another easy example, just to make sure that we are on the right page. And this one is the same way you find the characteristic polynomial, and this time the coefficient of the highest derivative is not 1. So this one maybe we can write 3m plus 1 square equals 0. So 3m plus 1 equals 0, and it is repeated, so I am going to write m equals minus 1/3 comma minus 1/3, and you see it is just a slightly different algebra, but the procedure is the same. And if I want to write down the general solution, c2 times x e to the power minus 1/3 x. Okay, so what's next? The next one I'm going to discuss about the complex conjugate case. Okay, so I know in one lecture covering all three cases perhaps may be confusing to some of you, but you can pause the video and watch in a separate in a different time to refresh your knowledge. But now assume that now we have understood how do I find general solution of a second order linear differential equation with constant coefficient. So in the first case, I may have two roots of the characteristic polynomial which are distinct and real. In the second case, we have two roots of the characteristic polynomial which are repeated, or in other words, which are equal. Now in the third case, the characteristic polynomial has two complex conjugate roots. So a good and easy example is the following: a simple second order differential equation, but this equation is very important one in science and engineering. We will see it later. Y double prime plus 4y equals 0, and characteristic polynomial m square plus 4 equals 0. And you see this one does not have it. I have chosen this intentionally, that it does not have the first derivative term. That's okay. It does not mean that we will always have first derivative term 0 for complex root. I'll show you other example. So you have m equals plus or minus I times 2 or j times 2 depending on your discipline. It does not matter. I is square root of minus 1. Okay, so now this is in the form of general form of 0. The real part is 0 plus or minus I times 2. You can also think of this way. So I have not, perhaps in this video I have not told you how do you deal with the complex conjugated case. So in order to find the general solution, general solution, you look at the complex. Well, obviously I think first you're going to you can think of this way. There are two roots. So because we are thinking e to the power mx is a solution, so the first one will be e to the power I 2x and plus second one will be c e to the power negative 2ix or I to negative x. And this is something okay, it is correct, but we do not want a complex number in the solution. So we want a real number, so we can manipulate that, and then that takes some time to manipulate that, convert it to a real number. So which I want to avoid. So instead I want to show you a trick. So what we do here is that we take the excuse me, we take the real part of m, so which is 0. So we say e to the power 0 in this case, and then we go by saying that times the complex one will take sine and cosine. So c1 cos 2x plus c2 sine 2x, and e to the power 0 is e to the power 0x. So maybe I can explicitly write e to the power 0x, but now it is not needed here because 0 times x is 0 and e to the power 0 is 1. So it's c1 cos 2x plus c2 sine 2x. So when the roots are, you don't need to discuss in a separate case when the roots are purely imaginary, but you just follow the same strategy. When roots are purely imaginary, then the e to the power, the real part times the factor becomes just 1. Okay, so maybe we go for a second example that does not have the real part 0, so a full complex number. So the characteristic polynomial for this differential equation is 2m plus 2m square minus 2m plus 5 equals 0. And you can use just the quadratic formula minus b, so a m square plus b m plus c, so minus b plus or minus square root of b square minus 4ac divided by 2a. Okay, so 2 plus or minus square root of, just simplify this, negative 2 square is 4 minus 4t divided by 4. So you can simplify this. You can see that square root of 4 minus 4t is square root of 36 negative. So I plus or minus I, 36 square root is 6. Now 2 plus or minus I times 6, you can cancel out a 2, so you get half plus or minus I times 3 divided by 2. Okay, so now it has a real part which is half and an imaginary part which is 3 over 2. So the general solution will be written as e to the power real part of m, which is half x, times c1 cos 3 over 2x plus c2 sine 3 over 2x. And that's all, and hopefully it is now clear how do you solve second order linear differential equation with constant coefficient. I have covered all three cases. In the first case, your characteristic polynomial has two real distinct roots. In the second case, your characteristic polynomial has repeated or equal roots. In the third case, characteristic polynomial has complex conjugate roots. And a different differential equation that I have not put in example could just have a little more complicated quadratic formula, but how complicated it could be? It could be just different numbers. So I don't think you will have any troubles in solving any of the second order differential equations with constant coefficient. Thank you very much for watching.